Hello, today we're going to talk about solubility. So just to review, solvation is when the solvent surrounds the solute. In the case of an ionic compound, you might have a positive ion like potassium being surrounded by water molecules, and the positive side of the water molecule will be away from the potassium. The negative side of the water molecule will be attracted to the positive charge on the potassium. So the process of the water, which is the solvent surrounding the solute, is solvation. Sometimes we also call it hydration, but I think solvation is the more accurate term. And the extent to which a solute will dissolve in the solvent is called solubility. Different solutes will dissolve to different amounts in a given amount of solvent. For example, if you have just a cup of water, you can only dissolve a certain amount of salt, but if you have a whole gallon of water, you can dissolve a lot more salt. Or if you're thinking about, a lake, you can dissolve a lot more salt. So the amount of solvent matters, but also when you're comparing one solvent to another solvent, that will affect how much can dissolve as well. So certain substances are going to dissolve better in water than others, and it really depends on their intermolecular forces. Ionic compounds tend to dissolve pretty well in water because they can form ions that interact and form ion-dipole interactions. Polar compounds tend to dissolve really well in water because it can form dipole-dipole interactions. But nonpolar substances will not dissolve very well in water. They might dissolve a little bit if they have significant London dispersion forces with the water molecule, but not so much else. Now don't forget that there's three things that have to happen for something to dissolve. So the interactions between the solvent and other solvent particles have to break. Now breaking bonds of any kind is endothermic. Or there's energy that is required to use energy to break the solvent-solvent interactions. Now, you have to also break the attractions between the solute particles. And again, since that's breaking bonds, that is endothermic, and which requires energy. And then finally, the solvent has to form new interactions with the solute, and that's forming new interactions. And anytime you're forming bonds, that's exothermic, which releases energy. So we say endothermic, this is positive because it's putting in energy. Exothermic is negative because it's releasing energy. So whether or not a substance will absorb or release energy when it is dissolving in the solvent depends on these three things. If the energy required to break the bonds is greater than the energy released when forming, then the whole process of forming the solution will be endothermic overall. So we'll absorb energy from the surroundings and it will feel colder because it's taking in energy from the surroundings. Now in the reverse situation, if it releases more energy when forming those interactions than it takes in when breaking the interactions, then it will be negative overall. It will release energy when it's dissolving. So, but if they're about equal, then you won't see any energy difference really. This also kind of informs us how some things will not dissolve. So sometimes the attractions between the solvent molecules are so strong that the solvent cannot form more interactions with the solute particles because those new interactions are not strong enough. So a good example of this would be if you have water as your solvent. Those water molecules are very tightly held together with hydrogen bonds. If your solute is something very nonpolar like oil, which is held together within itself by intermolecular forces, so dispersion forces. The dispersion forces that it could form with the water molecules aren't really enough to break the hydrogen bonding in water. And so that's why you form two distinct layers when you have oil with water. Now, some ionic compounds are actually not soluble in water, or only very little soluble in water. And from that, we can come up with these solubility rules, or solubility guidelines, really. And there's an acronym. It's SHAN1. And really the priority is from the bottom to the top here. So we'll start with number 1. Ionic compounds that have group 1 metals, that's where the number 1 comes in, are soluble. They will dissociate in water. Okay. Ionic compounds that have nitrates. Nitrates is NO3 negative. If you have that ion in the ionic compound, it will dissolve in water. Excuse me. A stands for two things: ammonium, which is NH4+, and acetate, which is C2H3O2. If you have ammonium or acetate ions in your ionic compound, it will dissolve in water. The fourth rule is halogens, those group 7 elements, fluorine, chlorine, bromine, iodine. If it has a halogen in it, it will dissolve in water, except if that halogen is paired with lead, mercury, or silver. So for example, if you have silver chloride, that will not dissolve because it's an exception. But if you have magnesium chloride, it will dissolve. Now our last rule is S for sulfates. Sulfates is SO4 negative. If you see SO4 negative in your ionic compound, it will dissolve with a few exceptions. So there's 6 exceptions: lead, mercury, and silver, just like with the halogens, but also calcium, strontium, and barium. So if you see like lead 2 sulfate, that compound will not be soluble in water. But if you have something like magnesium sulfate, that will be soluble in water. So it just depends on what it's attached to. Now these are more like guidelines, right? So each of these things that is an exception, or if it's just not on the list, that means it's only minimally soluble in water, only dissolves just a teeny tiny bit. But everything that is on this list will dissolve a lot, and we can assume it completely dissolves in water. Okay, so for this example, we need to draw a molecular level diagram that shows what happens when the following reaction takes place. We have a bunch of aqueous ions, and then some of them react to form a solid product, and the other ones remain aqueous. So I'm going to do like this. I have Pb2+ ion. I have 2 nitrate ions. I want to leave the polyatomic ions together. I've got our sodium ions. And I have the 2 chlorine ions. Like that. So they're all aqueous. And really, you could put them in separate containers, but the way that this is written, it just kind of says that they're all together. But right now, those are our ions in the mix. Now, what changes is that the lead and the chlorines come together to form a solid product. And solids will always sink to the bottom of your container. So you want to show that the lead is now attached to the chlorines. And it should be at the bottom. But I still have my 2 nitrates floating around in the solution. The circle is not big enough. And I have my 2 sodium ions still floating around in the solution. So just be really clear when things are bonding that they're touching, and then when you have a solid, it's sinking to the bottom. Aqueous things should be floating around in the solution.